Hello all, this is a follow-up video on my multiple LED circuit. We're going to be working on a new type of configuration today to run multiple LEDs known as a series circuit configuration. This is different than the parallel circuit configuration we had in the previous video. So let's go ahead and get started. So in today's video, we're going to talk about running multiple LEDs using what's known as a series circuit configuration. This is different than the parallel circuit configuration. If you recall in the previous video, for a parallel circuit, every single LED has its own resistor to limit current. The series circuit is different in that you only need one resistor instead of one for each LED. There are some benefits and there are some drawbacks. The series circuit configuration here is similar to Christmas tree lights, where each LED is going to be wired to the next LED. One of the downfalls, though, however, is that if one of the LEDs fails, they all fail. But one of the benefits is that you only have to use one resistor for the entire circuit. So we're going to go ahead and go through this in a little bit more detail. I'm not going to cover what each symbol means. Hopefully you've watched the previous videos to see what each symbol means in the diagram. So again, we're going to use 3 LEDs for this example, a red, a yellow, and a blue. We have the values for these LEDs from our spec sheet, and they're written down here in the diagram. So we'll be using those values when we figure out our total resistor value for the whole circuit. So in this circuit, we're going to be using a 9-volt battery pack, which is nothing more than a 9-volt battery I'll be using, one resistor to control the current for all of the LEDs, and 3 LEDs, D1, D2, and D3. The first LED will be red, the second will be yellow, and the third will be blue. So as I said before, in a series configuration like we have here, you only need one resistor to limit the current. However, we have to add up the voltages required for all of the LEDs. So we have to keep that in mind when we start putting LEDs in this circuit, because the total voltage of all of these LEDs cannot exceed the total voltage of this battery that we're going to be using. So we're going to go ahead and go through this. So again, we're going to come out of our battery positive into our resistor, out of our resistor into the first LED, the red LED, on the anode side, also known as the positive, out of the cathode side, which is the negative, into the positive of the second LED, which in this case is the yellow LED, out of the negative side of this LED into our third LED, which is the blue LED, out of that LED back to the battery on the negative side. So to compute the value of this resistor, we need to know a few things. So we come down here. For the red LED, we know that its maximum current is 0.02 amps or 20 milliamps, and its voltage is 2 volts. For the yellow LED, its maximum current is 0.03 amps or 30 milliamps, and its voltage is 1.8 volts. Ignore the mistake here, this should be 30 milliamps. For the third LED, the blue LED, the maximum current is 0.02 amps, 20 milliamps, and its voltage is 2.8 volts. Now, when we do the formula, we have to pick a maximum current for the circuit, and that's based on what the LEDs can handle. So this is going to be based on the weakest LED. In other words, we're going to use 20 milliamps as our current for the whole circuit. The reason being, if we decided to pick the 30 milliamp or the 0.03 amp, we would damage the other 2 LEDs as they can't handle that much current. So this circuit is also going to be limited by the LED that has the least amount of current going through it. So we'll go further into that now with the formula. So the formula states, for any resistor in this circuit, or even in a parallel circuit, as before, the standard formula says the resistance is equal to the voltage of the source, in this case our 9 volts, minus the voltage of the LED or LEDs, plural, divided by the maximum current of the LED. So in this scenario, we have to take into account the voltage of all 3 LEDs. So our voltage LED here is going to be the total of all 3 of these, and you'll see that in the formula here. So resistor is going to be equal to our 9 volts minus our voltage of total LEDs divided by 0.02 amps, because again, we're going to set the maximum current to 0.02 because that's all that D1 and D3 can handle. Even though D2 can handle 30 milliamps, the other 2 cannot. But we need to figure out the total voltage. So the VL, total voltage for the LEDs, is going to be the total of all 3 LEDs, 1, 2, and 3. So our red LED is 2 volts, our yellow is 1.8 volts, and our blue is 2.8 volts. So when we add this all together, we get a total voltage of 6.6 volts. So now we come back to our formula. Our resistor is going to be equal to our 9 volts minus our total voltage, 6.6 volts, divided by our total current, 0.02 amps or 20 milliamps. The resistor is equal to 2.4 volts divided by 0.02 amps, which gives us a total resistance of 120 ohms. So this one resistor by itself will need to be 120 ohms to keep the current at a 20 milliamp maximum to provide enough power and protection for all 3 of these LEDs. Let's just cover a note that I have here on the bottom of the sheet before we bring the circuit out. And I've said it before, but it's just good to have repetition. In a series circuit configuration, the voltage of all the LEDs combined must be less than the source voltage of the circuit also. The maximum current, I, is based on the LED with the lowest amount of current. So hopefully didn't go too quickly there and that makes some sort of sense. So here's our circuit and here's our battery. And let's just go ahead and run through this. 9-volt battery, we're going to have a negative and a positive. Here is our 120 ohm resistor, which our positive will flow into here, out of this resistor into our first LED, the red LED, out of the red LED into the next LED, which is our yellow, out of our yellow LED into the next LED, which is blue, out of the blue to the negative. So we're going to go ahead and hook the battery up, and hopefully this will work seamlessly. So we're going to put our negative in first, and then we're going to hook up our positive, and there you have it. So what's happening again is that we're coming out of the positive side of the battery with 9 volts through this 120 ohm resistor into our first LED. When it comes to here, it drops 2 volts. Then it proceeds into the yellow LED. When it comes through the yellow LED, it drops an additional 1.8 volts. Comes out, comes into the blue, and when it comes out of the blue, it has dropped 2.8 volts more. So by the time it leaves here at 9 volts and arrives at the end, we have dropped a total of 6.6 volts, leaving us with 2.4 volts left over of power. Now, we could, in theory, put a 4th LED in as long as it uses less than the 2.4 volts that we have remaining. So you can see where this circuit is dependent upon the size of the battery or whatever you're powering it with, because the total voltage of all these LEDs can't exceed this battery or it won't work. The other thing is, I mentioned this was like Christmas tree lights. If any one of these 3 fails, the entire circuit collapses, and I'll show you what I mean. I'm going to take the yellow out to simulate a failure or a burnout. And immediately you see that the circuit fails. However, once we replace it and put it back in, our circuit is reinstated. Hopefully this was clear. In a future video, I will show a hybrid circuit, which will be the combination of a series circuit like this and a parallel circuit as we had in the previous video. And then going forward, if this is interesting and is helpful, I'll probably do a video on an RGB type setup with LEDs and how to control them. Thanks again for watching, and see you next time.